Welcome to the first colloquium of the year. We're pleased to have so many here, and we're pleased to have Joe Hundley back from the uninhabited wastelands of the East. He saw many strange creatures there, I'm sure. He will talk today about Lie groups and Unitarity, and we're glad to have him.
Thanks very much, Leslie, for that fine introduction and for all the work that you do to organize our department colloquium. All of you for coming. This talk's try to pick something which I thought would be of the most general interest. So I picked something that basically automorphic forms that's mainly interested in people, mainly driven by the interest of people who go through automorphic forms. So this is, if I get to the last slide, which I hope to, will be a report on some things I'm doing with Stephen Miller of Rutgers University. So first to begin with sort of a survey of what Lie groups and their unitary representations are and why one might be interested in them. So first, here's what a Lie group is. It's a group which is also a differentiable manifold such that both structures are compatible. So the group thing means that you can multiply elements. I should mention at this point that if you want to keep something in mind, keep your favorite group of real matrices in mind. So for example, the group of all invertible real matrices. That has the structure of a group because you can multiply and invert its elements, and it has the structure of a differentiable manifold since it's a nice curve, say in one or more variables. Put differently, it can be covered with coordinate charts, such that each one of them is a little piece of Rn, and the maps where they overlap are actually polynomial, which certainly means that they're infinitely differentiable. So Lie group has both an algebraic and a geometric structure, and the compatibility is the statement that when you multiply things which you should think of as matrices, or invert things which you should think of as matrices, what you have is a C infinity map, provided you stay away from alpha matrices that are invertible. So they were introduced by the Norwegian mathematician Stephen Lie, and his motivation was actually, I learned this was to mimic Galois theory. So Galois had studied solutions of algebraic equations, zeros of polynomials, and obtained a number of results which are now celebrated with the course 419, such as the fact that you can square the circle or double the cube, or with a ruler and compass, or write down a formula that involves only algebraic operations, including radicals, for the roots of an arbitrary fifth degree polynomial, including that one, unless I have a mistake coming up. Lie wanted to extend these ideas. Okay, so a key component of Galois' work is to attach to each polynomial a sort of symmetry type, which is a finite group that acts in the zeros of this polynomial and tells you information about what the roots will be. So some conditions on what types of numbers can arise in this polynomial, which can give you information such as a fifth degree polynomial like this one can't possibly have roots that look like a formula in terms of plus and division and fifth roots. The zeros of that polynomial can't be of that form because you can say something about what they're like. So Lie wanted to extend these ideas to solutions of differential equations, and hopefully obtain simpler information. But what he figured out was that symmetries of differential equations weren't going to be finite groups. Right? They would be dependent on one or more complex parameters to specify an element of such a symmetry group. They would be what we now know of as Lie groups. Okay. All right. So now I want to sort of mention some of the other reasons why you might be interested. Well, they're interesting in geometry, and can be perhaps becoming more and more central in geometry. You're actually the expert on that. But around the same time, Felix Klein was proposing that the best way to understand the sort of at that time hodgepodge of different alternative non-Euclidean geometry was in terms of group theory, that each one sort of had a transformation group acting on a space, and the geometry was invariance properties relative to the action of the transformation group. So, for example, if you consider the transformation group of rigid motions of the plane, things that preserve the standard notion of distance, then you perform anything that preserves distance. It sends circles to circles, it sends lines to lines, and it preserves angles. But if you work with projective geometry, well, you can't really talk about what a circle is, because the same structure might be a circle based on one way of projecting, and not we can perform a projective transformation. So circles sort of just aren't a concept in projective geometry, because they're not invariant under the group of projective transformation. All right, I also want to mention quickly, a lot of the motivation for Lie groups comes from physics. So hopefully, and here's where I'll probably say something wrong about this. But the differential equations that Lie was interested in trying to extend Galois theory to were mostly motivated from physics. The sort of geometry and Lie groups have become even more important since Einstein came up with the idea that probably what's going on is that space-time is a curved manifold. And of course, they've been showing up recently in string theory as well as other attempts to come up with a unified theory of physics. They also show up in number theory, which is how I come to it. So those who've been attending the other seminar have to have seen that we have these functions called modular forms, which are periodic functions on the upper half plane, also with a generalized periodicity condition, that tend to have interesting number theoretic information, such as divisor sums and representations of numbers of quadratic forms embedded into their Fourier coefficient. The connection of these with Lie groups comes from the observation that the upper half plane could be identified with the quotient of SL2R by its maximal compact subgroup. And this leads to a better understanding of the generalized periodicity property of modular forms, as well as some other results in that direction, and a natural avenue of generalization, because you ask what happens if you replace SL2 by some other group. And the final reason why one might be interested in Lie groups, or perhaps things that came out of Lie groups, because is that they actually fed back not only the number theory, but even into the theory of finite groups. What happened was people discovered new structures while trying to classify Lie groups. These are the exceptional groups that we'll come to in a bit. And each of them, it was then proved that each of them could be realized actually as a group of matrices. So as a matrix group with defined by polynomial equations. Moreover, and this is a bit stronger, you can arrange for the coefficients in the polynomials to all be integers. And that's interesting because now you could interpret the same polynomials in your favorite other numerical structure. So a field is any structure in which you can add, subtract, multiply, and divide by everything except 0. And some of them are finite, and these are important in things like computer science and coding theory. And there are also, I mean, if you consider matrices whose entries come from a set with 27 elements, then the number of matrices is going to be finite, and you've just got a finite group. So if you have a new way to generate matrix groups, which Unitary turned out to provide, well, then you can sort of reverse engineer some interesting finite groups in that way. I should mention that this idea that, okay, if I have a Lie group, it's related to a matrix group, and in this matrix group, you can arrange to have sort of a Z structure. Arrange to have it defined by polynomial equations with entries in Z. These are Chevalier groups. It doesn't exhaust the Lie groups. Every Lie group will be related to a Chevalier group. And sometimes from now on, I'm going to restrict attention to them. So they don't exhaust Lie groups, but they exhaust the ones that basically we can then put back in to number theory. which, as I said, I come at this to number 3, so it's going to work with Chevrolet.
Okay, so it sounded for a moment like you were saying that all Lie groups are represented up to something rough by the list of Chevrolet groups. Is that true?
Yes. So there's a classification of Lie groups that attaches an invariant. And this is sort of a map with fibers, and each fiber contains a Chevrolet group. And I suppose I should mention that if I have polynomials with integer coefficients, then I don't even really need to be able to divide. So when I mentioned a second ago that we could work in any field, system of numbers where you can add, subtract, multiply, and divide, well, you could even work in a system where you can't divide. You will, however, need these two elements, 0 and 1, because you'll need the identity matrix. Okay. Now, groups in general, and I think this is true, groups in general and Lie groups in particular really show what they're there for when they're acting on something. So perhaps when they're the symmetries of some other object, like a vector space or a manifold or some structure inside of a vector space or manifold. A representation is an action of a group on a finite or infinite dimensional vector space by linear transformation. When the original object of study was not a vector space, there's often vector spaces associated to it. For example, if you were interested in topology, you might consider cohomology groups, or homology, or spaces of functions defined on your manifold. The action on the manifold would reduce an action on functions and forms and so forth. A unitary representation is one where you have an invariant, positive, definite Hermitian form. So, what's the details of this? This is sort of an inner product. Now, so that it's, when you reverse the order, it's conjugation. So we can think of this as taking, the simplest example for this would be to take column vectors with complex entries and do, say, x transpose times y bar. So it'll be conjugate linear in the second argument. And perhaps the better example to keep in mind, because it's, well, as I said, we maybe start with something geometric and then we'll get past the spaces of functions, is to say that you think of your vector space as being a space of functions, say, square integral functions. And then you can integrate f of x, g of x bar, provided you know what dx is. And then you'll have a bar over this. So this is sort of a good example of what is a unitary representation. So unitary representations, like Lie groups, are an interesting number of different points of view. My preferred way of thinking about Fourier analysis. So Fourier analysis, of course, has lots of applications, breaking up a wave into fundamental waves. And so the Fourier series is a way of thinking about decomposition of a function as Fourier series, or a square integrable function of the Fourier series, is that L2 of the circle is a unitary representation of the circle, which decomposes as an infinite direct sum of irreducibles. The irreducibles are the spaces spanned by the basic harmonics e to the in theta. And so the fact that any element of this unitary representation can be expressed as a convergent infinite linear combination of those is sort of a representation, a simple representation theoretic decomposition of the unitary representation. The next, and another good one to keep in mind, is L2 of R. R is also a nice space. It's a Lie group. Right? Both of these are actually Lie groups. And this time it's the Fourier transform. Right? So we have more basic harmonics, e to the itx for any t. It's interesting to note that those are not square integral. So you decompose the unitary representation L2, and it comes out with actually a direct integral of other things which individually are not in it. But in terms of representation theory, that's the spectral decomposition of L2 of R as a unitary representation. The other things was sort of for motivation, that there's a reason why people focus so much on unitary representations and the question of whether a given representation is unitary, is that when you do quantum mechanics, you'll have a state space. The state space is a Hilbert space, so you'll have a Cartesian form, and your representation is only going to sort of be useful for thinking about it if it's respecting the Hilbert space structure. So the unitary representations actually appear as quantum states in quantum mechanics. In number theory, we tend to study the space L2 of GR mod GZ, where G is now one of these Chevrolet groups. It has to be, if I want to talk about, what it means, what G of Z means. There are polynomial equations which define it, and we can take the integer matrix. And we can think about this space. Now, this tends to be a nice space. It has an invariant measure on it, which comes from measure theory on the Lie group G of R, but it's a finite measure, unlike G of R, which is in general an infinite measure. And so when one looks at the decomposition of this unitary representation and finds interesting number theory inside of it, basically coming from the fact that we have this discrete subgroup G of Z. Actually, if we take the special case where G is SL2, well then this is another way of thinking about the modular form, which we mentioned earlier. So, of course, this is a unitary representation because it has that invariant as a product on it. I suppose I ought to mention that if I want to think of this as a representation, I should say how what the action is. And the action is by right translation. So if G is an element of G of R and F, well, this actually makes sense for any old function, but right now we're thinking about L2 of GZ mod GR as a representation of G of R. Well, then the right translation of this should be another element of the same space. I can tell you what it is if I tell you what the value of X is, and the value of X is the value of F at XG. So that's right translation. Since the G of Z is on the left, it's well defined on functions which are defined in GZ mod GR. Yeah.
I don't understand GZ mod GR. So
GR mod.
is GR bigger?
Oh, yeah, sorry, I'm just reading it left to right.
Oh, okay.
That's a backslash. So
Okay,
yeah.
all right, okay, so all right.
Yeah. Okay, so this is kind of interesting because it means that there are a number of conjectures in number theory that amount to conjectures about either what the set of unitary representations looks like, or which unitary representations can actually appear here. And so advances about our understanding of the unitary dual, which is what one calls the set of all unitary representations of a given group, can lead to advances in number theory. What's kind of interesting is that it's also true the other way. And this is what we're going to, I hope to discuss later, is that sometimes you can actually use number theoretic constructions to prove theorems in Lie theory that are hard for people using purely Lie theoretic methods. Now, the next thing that I wanted to do was delve a little bit into some beautiful aspects of the classification theory and how the five exceptional groups were seen to exist. So this phrase is actually, it's literally true. People were trying to classify actually semisimple Lie algebras, but it's equivalent to classifying semisimple Lie groups. And was the first step for classifying. And thought they had a complete list. And at some point they found another infinite family. And then they again thought they had a complete list. And then they found another one. And after some attempts to prove that it wasn't really there, they could be ruled out on some basis, they determined that it really was there. And so the question was, well, whether one could see it in some reasonable way. Eventually, reasonable ways to understand this first discovered thing which is now known as G2. well, I'm getting ahead of myself. So I want to delve a little bit into the classification theory of these groups and how the exceptional groups are taken. So the first thing is that you can sort of divide Lie groups into the ones that are semi-simple and the ones that are solvable. And this is sort of based on things about the commutator subgroup, which is often known as G prime. So this is just a subgroup of G that's generated by all commutators X, Y, X, and X, Y inverse. And so a semi-simple group has the property that it's its own commutator, at least if it's connected. And solvable groups are at the other end of the spectrum. They have a chain of subgroups which terminates at the identity, such that you start with the group G, you take its commutator, you take the commutator of that, you take the commutator of that, and it terminates at the identity. So it's sort of the opposite of semi-simple, because semi-simple is stable under this operation. And a general Lie group you can fit into an exact sequence. In other words, you can find a nice normal subgroup which is solvable, such that the quotient is semi-simple. And so that's, in a way, breaks the problem of classifying them into the problem of classifying solvable ones and the problem of classifying semi-simple ones. Now, the problem of classifying solvable ones turns out to be really hard, so it's not yet solved. Which is kind of ironic, given the name. The problem with classifying semi-simple ones has a beautiful solution, which I'm going to delve a little bit into the details of. Okay, so it was solved by Wilhelm Killing, is the key person in this story, and attached a beautiful combinatorial invariant to each semi-simple Lie group, which is a finite set of vectors with a finite group of symmetries. And this is called the root system. So I want to sketch the basic ideas and try to illustrate them with the example of SLNR. And the first thing is that I need to introduce the Lie algebra. Now it's time to. Now the manifold, well, picture a manifold. The picture is a curve in space, right? Sometimes it's five-dimensional, but still this is what we can visualize. And at each point, it's got a tangent plane. Okay, a Lie group is a manifold that has tangent planes, or tangent spaces of dimension equal to the dimension of the group. And the group structure is going to put an additional structure on the tangent space of the identity. This is the Lie algebra. The tangent space of the identity is called the Lie algebra. It has an additional algebraic structure called the Lie bracket, which I won't really need here, so I haven't written it up. The usual notation is that the Lie algebra of G is the f of G, lowercase f of G. And if G is a group of matrices defined by some equations, then its Lie algebra is sort of differentiates the equation. So if this equation defines a group which, together with being not determinant non-zero, this equation does define a group called the orthogonal group Q. Then when you differentiate, well, because of the chain rule, you plug in the identity with this. The condition that the determinant is 1, well, think of this as the product of the eigenvalues, and if you differentiate that and then plug in the identity, what you get is the sum of the eigenvalues. And so it's very simple, well, the determinant of 1 is 0. This is the idea for the Lie algebra. So this will be an actual vector space of matrices, and of course vector spaces are in many ways more convenient than manifolds. So we just linearize the number of provinces. Now G acts on its Lie algebra, and we continue to think of G as a group of matrices in which case its action is just conjugation. Okay, so now if I want to continue with these ideas, what I do is I take a maximal connected diagonal subgroup, which I can go ahead and think of these as matrices, and I can go ahead and think of this as the set of diagonal matrices within G. And my main example is the group is the case when G is SLN. I've chosen SLN even though it's slightly less convenient than GLN because because the commutator subgroup of GLN is SLN. So if I want something that's commutator with itself, I can take SLN. And I can just take T to be the diagonal elements. And what you do is you let T act on the Lie algebra of G and look for eigenspaces. The elements of T will commute with one another, so they're going to be simultaneously diagonalizable. And if I've taken them to be diagonal, they're basically already simultaneously diagonalized. So, for example, if I want a basis for SLNR, well, I can take Eij to be the matrix with a 1 at the ij position, 0 at the rows. That's in SLNR because its trace is 0 unless I happen to equal j, in which case I can say subtract 1 over x times the identity matrix and have to put the trace 0. And so when I conjugate by a diagonal matrix, well, these are all fixed. And here you multiply by, well, if your diagonal matrix has entries t1 up to tn, then it multiplies the ij by ti over tj. It's sort of more convenient to linearize again by taking the differential, right? The differential will be a linear map on the tangent space of t. In this example, the torus t is instead of diagonal matrices of determinant 1, and tangent spaces instead of diagonal matrices with trace 0. And you get a family of linear functionals. Okay, so the linear functional corresponding to doing ti over tj, there's a natural map from the tangent space to the diagonal matrices themselves, which is just matrix exponential. So this sort of looks like taking a logarithm. Really what it is. So this way, what we have is basically n times n minus 1 non-zero linear functionals on n minus 1 dimensional vector space. So that's our finite configuration of vectors in a finite dimensional vector space. And note that I threw away 0. I mean, 0 appears as an eigenvalue for this action because this is the 0 eigenspace, but we want the non-zero. Now, what's this finite group of symmetries? Well, if you think about it, the normalizer of the torus. The torus is T is called the torus. This group of diagonal elements. Because in certain complex groups, it actually is a product of several circles, which is to say, it actually is a topological torus.
Product of complex circles.
So for complex Lie groups, it'll be a product of complex circles means C cross, right?
That means, yeah, I guess so.
Yeah. So if I take a complex Lie group, I'll get a bunch of copies of C cross. If I take a compact Lie group, then I get something that is real. Then I actually get a bunch of copies of the unit circle. I think compact Lie groups were studied first, and that's how the torus thing came in second. So these non-zero eigenvalues are called the roots, right? And we're just thinking of them as linear functionals in the algebra of the torus. And so, but each of them is, of course, associated to sort of a homomorphism from the torus itself, something like this. And I want to convince you that the set of homomorphisms obtained in this way is always, its elements are permuted by the normalizer of T. So this isn't too hard to see, because if I have an element that normalizes T, say call it n, and I have a vector x in the Lie algebra on which T acts by some scalar value function like that. It actually be a scalar value homomorphism. Then what's going to happen if I look at an xn inverse? Well, I can just put an n inverse there and an n inverse n there, and then I'll have n inverse Tn, which is another element of T because n normalizes T, and so I'll get exactly this set. Okay, so this means that if you look at this set of vectors, it's stable under the action of the normalizer. Of course, T itself acts trivially, because if T is an abelian group. If you conjugate, if you take n to be in T, then NTN is T itself. So T itself acts trivially, and so you get the quotient of the normalizer of T by T itself. And that turns out to be a finite group. So just to see that in an example, it's not too hard to check that if you take an n by n matrix that normalizes the group of all diagonal matrices, then it has exactly one non-zero entry in each row and column, which is to say that it's a diagonal matrix times a permutation matrix. So that when you quotient by the group of diagonal matrices, what you get is something that's isomorphic to the group of permutation matrices. Now, a permutation matrix acts on a diagonal matrix by permuting the entries. And we can think of this as acting on the coordinates ti or tau I by permuting the indices. And now we can sort of see that if we have all these functionals ti minus tj, permuting the indices permutes those functionals amongst themselves. Something else which bears mentioning is that if you just have a simple transposition, a simple type of permutation that reverses I and j, leaving everything else fixed, then it fixes an n minus 2 dimensional subspace of the space that the root's in, right? Because it fixes all of the coordinates except those two, and it reverses those two. So it's sort of a reflection, a geometric reflection. So take the point, take the distance to a hyperplane, and continue that same distance out from the other side. Okay, this is a general picture. Right, so this is how you attach to any this finite set of vectors with Lorentz symmetry. These sort of satisfy three axioms, which are worth mentioning. So first, they span. Second, if I have an element, the only scalar multiple of x, which is also in there, is negative x. That's a self-negative thing. And you have a reflection, which sends each root to itself and fixes the hyperplane. And then this is the key fact, there aren't that many arrangements of such vectors. So this is the part that I thought would be interesting. It is to actually do the case when the dimension of the vector space is 2. So, so we have three conditions. We can choose a positive definite product, which is left invariant by each of the reflections. So we can think of our reflections as geometric reflections of the usual Euclidean plane, which are defined by basically this formula. The reflection in x sends y to x dot y over x dot x times 2, subtract that multiple x. All right, now one of the conditions is this fascinating integrality condition that this has to be an integer. And this is sort of where all of the beauty comes in. So this has to be an integer. And so does that, because I can reverse the roles of x and y. And if I multiply them together, I get this number. Well, I get 4 times this number. Moving 4 to the other side, I get this number. It has to be an integer divided by 4. But we learn in, well, Calc 3, if not before, that that is the square of the cosine of the angle between the vectors x and y. So that angle has to be, so that angle really is tied down an awful lot. And it's an integral multiple of pi over 2, pi over 4, pi over 6, or pi over 3, which I guess I could say more quickly by saying that it's an integral multiple of pi over 6. Oh no, pi over 4 is not as well. All right, go ahead. Okay, so if I take two vectors which are in a root system and are with nearest neighbors, A and B, so that will force the angle between them to be acute because it's obtuse, and reflect because it's an acute one. I can always reflect in the line perpendicular to any root in the system. And so it'll have to be pi over 2, pi over 3, pi over 4, pi over 6. And there's a little bit more, because you can say something about the ratios of the lengths between the two vectors. Because, so for example, if this number is 3/4, so that your angle is pi over 6, these two have to be integers. And so they have to be 1 and 3. Okay, so the only way to make that happen is to have the ratio of the lengths of the two vectors be the square root. So if your angle is pi over 6, then you have vectors of two different lengths sort of alternating, so that each one, let's say of length 1, is both of the two adjacent ones are of length the square root of 3. And each one of length the square root of 3, the adjacent ones are of length 1. And something similar happens for each of the other two. If the angle between them is pi over 4, then the ratio has to be root 2. If the angle is pi over 3, the ratio has to be 1. If the angle is pi over 2, you can't say anything about the lengths, but that's well, then you're in this situation. And what's really going on is that you have one root system that lives in this line and one root system that lives in this line, and they don't see each other. Okay, so for dimension 2, there are really only 4 possibilities. Here they are. And the first 3 were known. the first time this exercise was performed. That one is basically 2 copies of SL2. That one comes from SL3. That one comes from either an orthogonal group in 5 variables or a symplectic group in 4 variables. These are the groups that are defined by an equation in the form GQ G transpose equals Q. Orthogonal means Q is symmetric, and symplectic means that it's Q symmetric. And those types of groups will give you this one, but this one was new. And you can't rule it out because it's really there. And what's more, there's a group attached to it, which was discovered because, well, you can rule this out and see whether it was there. And then it's nice first because it's so nice that it basically uses 109, and it's also nice because it gives you sort of a flavor of a bit of history and then the flavor of the general classification. That you have 4 infinite families that come from Weyl families or matrix groups. The ANs come from the SLNs, and B and D come from different types of orthogonal groups, matrix groups that preserve a symmetric matrix. And then the C's come from matrices that preserve skew symmetric matrix. And those are the infinite families, and then you've got these 5 other group guys. And you can't prove they don't exist because you essentially prove that they do exist. And so that's what they're called. The largest is E8. It's a system of 240 roots in an 8-dimensional vector space. And if you saw the poster for this talk, then the picture on it is a geometric picture of those 240 roots projected into a certain 2-dimensional vector space. And if it looks very symmetric, that's because it is. This is the order of its symmetry group. And I meant to put in commas to emphasize how big it is. But it's big. So the vertices of that diagram are the 240 roots of the 8. With each one joined to its nearest neighbors. As you notice, there are a lot of lines in that picture because each one has a lot of nearest neighbors. You project onto a 2-plane. This is sort of a side thing. If you have a root system, you can choose a set of simple roots and then take the product of these reflections. And what you get is a rotation. And determines a particular plane that it's rotating in. And that's the plane that we projected into, which helps explain why there's an obvious rotational symmetry to the diagram. This is actually of order 3. All right, so now we're going to think a little bit about some problems in unitary representations of units. So Arthur has some lovely conjectures, which seem to be right, and if they're right, there's a really sort of surprisingly beautiful structure, both to the set of unitary representations of a Lie group, the thing that you get by replacing R by certain natural analogs of R attached to the primes, which are called other local fields, and also what these automorphic forms that you get by considering GR by G. All right, so fundamental of this is sort of this group. This is actually what's called the Weyl group of R. So it's a semi-direct product of C cross, and of course the Galois group of C mod R is just a 2-element group consisting of the identity and complex conjugation. So here we have a group that consists of pairs. Well, I can think of it as a group whose elements are C cross, and then another copy of C cross. And an element J, which conjugated across C cross gives you complex conjugation. So this can actually, if you're familiar with the Hamiltonian quaternions, you can think of it as the union of C cross and J times C cross, where J is the usual J in the quaternion. Okay. So we take the product of that with SL2Z and send it into a certain other group. So the classification theory of Lie groups actually tends to pair them up in a natural way. It attaches to each a root system. We'll delve that far into classification theory, but they come in pairs. So each diagram, each root system has a dual root system. And if we look at the fibers of the map that's in the group to a root system, then on matrix groups, you can pair up the elements of the fibers of that map as well. So that each matrix group has a dual group. And so we should be looking at homomorphism for each of the C points of the dual of the thing we're interested in.
Now, the Galois group of C over R, when it's written that way, it looks like something difficult. Am I missing something?
No, it's a two-element group consisting of the identity and complex aggregation. Yeah.
That's just what I hoped it would be.
Okay, so the problem that we've been looking at is related to Arthur's conjecture. For certain of these homomorphisms, we have an idea, of what the representation attached to it should be. And one would like to know that that representation is unitary. And one can actually get that it's unitary through our work with forms, which is a branch of number theory. So I'll talk about that a little bit. Now, the first specialization is that here I have a sort of complicated looking group, but this is a normal subgroup, so it has a quotient map onto this very simple two-element group. And I want to take parameters that factor through that. So then what does my element look like? Well, I can think of this as this two-element group consisting of one in complex conjugation, direct product with SL2R. So if you look at a homomorphism from a two-element group, well, its image is an element of order 2. That considers in terms of homomorphisms, of course. So now we're really looking for an element of order 2 in the dual, and a homomorphism from SL2C into the centralizer of that element of order 2. The other thing is that we can assume that the image of SL2C is fairly big in the sense that we will precise about in a second. And the other thing is that we can restrict to the 5 exceptional groups because the classical groups are already done. All right. So perhaps this homomorphism from SL2C across this two-element group is called a parameter. And again, this sense in which G check is dual to G you have to equip each group with a torus. You have to equip G with a torus, and then G check is equipped with the torus. And they're dual in the sense that, say, homomorphisms from GL1 into T, you can think of this as homomorphisms from C cross into the C points of T, are identified with homomorphisms from T check to C cross. Right, so that's a common feature of duality that reverses the order of errors. Now, our map, well, here what we really have is this gives us an element and this gives us homomorphism into its centralizer. And it turns out that, so homomorphisms from SL2, if you're considering them up to conjugacy, well, you can sort of pick an SL2 triplet. So it's sort of convenient to work with this element to the center. And that will give me an element of the torus. Meanwhile, the complex conjugation has given me an element of order 2. And I can assume that they're elements of the same torus. And then what I want to do is sort of cook up actually a homomorphism from the R points of T into the complex numbers based on that pattern. So the way that's done is by saying, well, the set of R points of T is really dim T copies of R cross. And you can split a copy of R cross into a copy of the positive reals and a plus minus 1. Now, homomorphism from plus minus 1 is sort of the same thing as an algebraic homomorphism of T taken mod 2, which means it's the same thing as an element of order 2 in T check, based on this identification from duality. And then a homomorphism of this part, well, this is several copies of the positive reals. The positive reals are identified by the exponential map of the reals, so this is really a vector space. And so it can be thought of as an element of of the Lie algebra of T check, or by exponentiation an element of T check or C itself. So this is why the two elements that we got from psi actually can be bundled together into a character of this group, with the character of this part coming from this element and the character of that part coming from the image of complex conjugation. All right. Then how do you build a representation from a character? Well, this will be well as the other representation theorists in the room is what you do is you consider an induced representation, which is just take the space of functions which are equivariant by your character on the left. So that if I put a B on the left, it comes out with that dependency on B. This is sort of a normal factor. Where I have to take with B is, so B is an extension of T. What you do is you say, I'm thinking of these matrix groups are committed to that. There's nothing wrong with it. I'm doing it. Right? T, I'm thinking of it as a space of diagonal matrices. I can certainly put it into matrices and then choose my basis so that they're diagonal, and then I can say that B is the ones that are upper triangular. So this ones that are upper triangular and have ones on the diagonal is a normal subgroup, and the quotient is identified with T. So that means any function from T to anything, I can pull it back to be a function from B to the same thing. In particular, I can take the character of T that I just constructed and think of it as a character of B. As mentioned before, this is how the group acts on its function spaces. Now, this space psi is not unitary. The goal is to prove that it has a quotient which is unitary. Now, here's the attack on the problem. What we want to do is put this into a space of automorphic forms. And to do that, well, we have to try and get it to here, or something that's a bit more convenient is to take this mysterious number system AQ cross, which is obtained by taking R, taking these natural analogs QP, which are alternate completions with respect to alternate topologies of rational numbers, bundling them all together into a big ring in which Q sits discretely. Okay. So that Q cross mod AQ cross can be thought of as Z mod R. Or Z cross mod R cross. But so in general, whenever you say A cross mod Q, A points mod Q points, you can generally think of it as being roughly equivalent to R points mod Z points. So the function that lives on that is like a periodic function. And what we want to do is sort of soup things up so that they can live here. Well, the sign character is a perfectly good character of R cross, and so if I can pass to here by sort of filling in what has to happen at each prime, so that I'll have something that's well defined on the quotient, then I can put this into automorphic form. There's a method to do that. So that's just sort of globalizing the sign character. Note that it does depend on a choice of a character of Z mod NZ that sends -1 to -1. So this is going to be nothing on this. Okay. But then having made such a choice, what we can do is identify the sign character. Well, this is a way of fattening up the sign character. This is on a bigger space. And it'll then give you an identification of the character that we constructed from psi, with the character that lives on the points of this matrix group, the torus, over a larger number system. So having done that, well, then we can repeat this equivariant space of equivariant functions construction, basically word for word, and get a space of functions that live on the Adele points. This thing is called the Adele ring of Q. The Adele points of the matrix that we started with. And so we'll get a nice space of functions that lives here. And of course, we can push them down a little there if we want.
So is this a new approach, or it is already used this kind of construction?
This way of proving unitarity is definitely. I think that I'm not sure whether it's been used on this particular problem before. I believe that Arthur's beliefs about what residues of Eisenstein series were going to be square integrable motivated the conjectures about which representation lead groups and chaotic groups would turn out to be unitary.
Mm-hmm.
So in that sense, yeah, it's one of these things where, yeah, the idea is not at all new. If anything's new, it's the fact that we, figured out how we wanted to attack that 700 million element group, and actually implemented the strategy on the computer.
And what kind of representations we get? They are unitary, and what else?
Let's see, I don't know. Yeah.
Or what they are not?
Yeah.
Do you know what they are not? They are not.
They are not something.
I don't
I mean, they're certainly they're language portions of.
So they are not square integrable.
They are. I don't know. I guess. Let's see. I don't know. I know that the residues of Eisenstein series that
If
you
they
get
are
are
not
square integrable on
close.
Wilson forms. But what we have is, yeah, they're Langland's quotients of
Then they are
principal
not-
series that are, I guess, on the walls of the dominant chamber.
Then they are not square integrable and not temperate.
Yeah.
If they are not quotient.
Yes, yeah.
Mhm.
Yes, if I'd been thinking better, I certainly would have said that they weren't tempered, because
Mhm.
that was the other goal of Arthur, is to sort of describe the state as non-tempered unitary.
Mhm.
At least a little bit. And of course, I'm cheating a little bit here, because here I have this sort of extra parameter. And what's going on there is that, well, we have a point that we get from the original parameter phi, which lives in a DMT-dimensional vector space. And in order to actually get anywhere, we can't start with the original point. What we have to do is view it as a point in the DMT-dimensional vector space, and consider certain meromorphic functions on the DMT-dimensional vector space. Poles, often poles of fairly high order, at the point that we were originally interested in. And then the residue, the passage from the full space of functions to the ones that actually show up with a non-trivial residue, is a quotient map. And if you can show that these residues are square integrable functions, well, now you've proved that you have a unitary quotient. So that's more or less the strategy that we've been able to push through in a number of new cases in the exceptional. I was thinking I would stop there.
So they get pockets with this construction.
I think so. But let's go with I don't. Miller is in touch with Adams and Bogan, and Adams and Bogan know about packets, and very well about packets, and particularly about specifics that are known for real movement captures and what the packets should look like. And that's where we're getting this list of things which we think are unitary and conjectures. And I should also mention that one other thing is that the other aspect of the communication about is that the Atlas group, the Atlas and Lee groups are sort of working on the same problem through a nicely complementary method, where we have a finite list of cases where we need to check unitarity. And the ones that are hardest from our approach are easiest from their approach, and vice versa. Our approach, it gets harder the farther you are from rho, and their approach, it gets harder the farther you are from 0. And these things are sort of spaced between rho and 0.
Any other questions? Thank you, John. There will be refreshments upstairs. Our next